Open-GIS, short edition. We're going to use a lot of different technologies. They're all open source. My code's available at GitHub. And this is the typical workflow we might expect, where people enter data through computers, maybe GPS devices, then the servers serve it up to the internet, maybe GPS applications. I'm going to take one branch of that and focus on grabbing stuff from the internet, these websites specifically, and serve it up to a GIS. Why do this? Because it's distributed. The police serve their stuff up to the internet, I get it from the internet, and as long as the links aren't broken, I can update this analysis at any time. So let's focus on the first script where we get it onto the local machine. It requires us to get to know our data. The SAC crime extracts are CSV tables within zip files. The SAC PD station houses are just web listed content, and the rest are shape files. So you go to the crime extracts reports page, you'll see zip file locations in a table. Well, I need to know the source code to automate this, so I created a function that uses regular expressions to pull out those zip file locations and find out that they're under the stats data directory, and I can access those zip files directly. The station houses, you'll notice the web page, there's that little map it next to the zip code. That's a link. Links to the Google Maps API, allows you to basically serve up a map. Well, I take that address and pull it out to the geocoding API that Google offers and get a JSON string in return. I can do XML, it's just another way of parsing it, and gives me the lat-long locations. As we'll see in the data cleaning, I'm going to build the crime table. The table looks like this initially. I add another column, and there's a 6% loss in the data because sexual assault doesn't have XY coordinates, so I just dropped them from the analysis. The codes there are 4-digit codes. They're the universal offense codes. The documentation shows they're grouped already into little 100 blocks, like 1301 to 1399 is assault. There's extortion, bribery, lots of different things. So I create a simple code to have 7 of those. It's a catch-all. And if I treat them as a continuous integer, I can break them apart and then stick them in those different bins, 8 being everything that's not going to have a specific number. And I create a table in R that basically gives them values as a lookup. So one's homicide, 8's others, kidnapping, assault, stolen vehicles. Then the result is a crime table that looks like this with occasion date, coordinates, and simple code, or the codes. Crime type lookup table. And the station house, I also grabbed the station house name. So let's load this into a database. R has SQLite functionality to create it and upload SQL commands to it. So I do a create table statement. SQLite uses different types of data types than other databases. Like instead of varchar, it has text, just has a generic int, and it doesn't even matter. You can put text in int fields. It'll work around it. It's very flexible, but that could be bad or worse, or bad or good, depending. I create some indices on the occasion date and simple code, as those will be what we look up. And here's the create table statements for the other 2 tables. And even on stations, I don't even put in data types because SQLite doesn't really matter. It doesn't really care. On my new PC I created for this video, it took me less than a minute or 2.5 minutes to get the data from the internet onto my computer in a database. But that database now needs to be made spatial, so here's a SQL script I created to do that. The first one's just make the command line pretty to look at. The second command reads in a SQL script. In this case, it comes with SQLite to initialize the spatial tables, like the spatial reference table. It gives you SRIDs that define projections and just inserts them into that table. Then I create 2 columns, one for the crime and stations table, and name them shape, give them a projection value, which I'll talk about in a minute, and then tell what type they are and the dimensions. The SRID I'm using is a EPSG code. 2226 is for the state plane, California, Zone 2. You can go to the spatialreference.org, learn more about it. Then I need to populate those columns. I use in a simple update statement, but now I'm using the geom from text SQLite command and feeding it a string, point, and fed by the coordinates of that table, and then defining their projection, and that populates the table. SQLite has these load shape commands that just load the shape file, give it a table name, and how you want to find the projection in the spatial field, the geometry field. And it basically defines the create table statement and loads the data from the DBF. And I create a spatial index, probably not necessary, but give it a try anyway. So what's next? Let's look at that workflow again. I'm going to now look at the GPS application part, where I'm going to map and do some crime density analysis. If we jump over to Open-GIS, I already have everything set up here. Block groups pulled from the SQLite database. Up here I click on this, just like ArcGIS, you connect to it, and I can build a query before I even pull it in, just like a definition, query in ArcGIS. I've already pulled those in. If we look at the general tab here, it shows sort of subset. You can do that query building directly. March homicides, I basically did a classification on the simple code and just kept only the first one. I'm not able to get the join because for some reason Quantum-GIS doesn't have the ability to pull attribute tables from a SQLite database yet, from what I can find out. And these are 3 different maps I made using grass commands like this. These are just command line statements that I can enter into the grass toolbox. Here I'm able to browse my grass database, which is actually separate. It's a hybrid system that's connected to my SQLite database. I can use different types of functions under these different settings, just like Arc Toolbox, or I can just grab a shell and enter commands directly, like the G region-P prints out the region information. I'm able to extract out the extent of my data, give it a resolution, and I can change that using the commands like these. So enter commands like these for kernel density, Voronoi map, nearest neighbors, and end up with something like this. The Voronoi map is like Delaney triangles. It draws polygons. Where they're smaller is where there's more density. Nearest neighbor, basically I created on 100 resolution, I gave a size of 500 or 5000. It's very big. As you can see here, you get these big neighborhood circles, and just counts them up. Where there's overlap, it's more dense. And the actual kernel density is much smoother than that, and you see the same pattern emerging though. So let's plot the actual March coordinates of all crime, and it kind of corresponds with it. As we can see, I'm not accounting for any kind of overplotting. March homicides, let's look at those specifically. There's 5 of them, mostly in southern Sacramento. And this is a basic introduction. If you want to learn more, visit my website. I'm going to have a full version of this video that'll be over 30 minutes long.